Mm, yes. Got it. Okay. I think now we should be live. So first, let me introduce our guest for the statistics seminar from the Federal University of Minas Gerais. It's my pleasure to present Abhirup Datta. I'm very confident that even though he's a very young statistician, many of you know his work in spatial statistics. He has working with the nearest neighbor Gaussian process, the Datta model, some extensions of those, and now he has providing a lot of literature, very interesting ones, at least on archive, where I can read for combining machine learning with Gaussian process. That is what he will talk about. Datta did his PhD under the supervision of Sudipto Banerjee, someone I'm sure all of you know as well. And then now he's at Johns Hopkins as an associate professor. As I put in his, minor bio, he has many awards and he's a very promising young statistician. So I'm very happy to have you here, Abhi. For us, it's a pleasure, and it's a great opportunity to listen to you talk and learn from whatever you have to teach us. So thank you very much for accepting the invitation.
Thank you very much, Marcos. Am I audible?
Yes, it's fine.
Okay. Thank you so much, Marcos, for the introduction and for inviting me to present. And good afternoon, everyone. Thank you for coming to the seminar. As Marcos said, my talk today is going to be about like combining machine learning methods, which have become like really popular nowadays, with some of the more traditional Gaussian process-based modeling for spatial data. That's kind of what my background was and what I'm more familiar with. And the motivation for this talk was that I was working on a different like spatiotemporal applications, and I was reading papers in environmental science journals, and I see that methods like random forests and neural networks are being used increasingly for spatiotemporal data. And because my training is more on kind of statistically modeling the spatiotemporal dependence, I was curious about how these methods account for spatiotemporal dependence in the data, and that's kind of the motivation for this talk. And I'm going to be delving into this issue in more details. So this is the outline of the talk. I'll give a brief introduction to the spatial linear mixed models, which is kind of the standard modeling framework for geospatial data. And then I'll talk about why some of these machine learning methods like random forest and neural networks have become so popular. And part of the reason is this linear term here, the linear word here in the linear mixed models, which these machine learning methods kind of relax, and they essentially do nonlinear regression, and often which gives better, more accurate predictions when analyzing data. And then I'll talk about how some of these standard machine learning methods can or cannot account for spatial dependence in the data. And then I'll present two new methods, one extending random forests to model spatial dependence, and the other one extending neural networks to model spatial dependence. And as you can see by the names of the methods, RFGLS and neural NNGLS, the GLS stands for generalized least square, something which is we know in linear models for dependent data, and we use the same principle to extend these machine learning models to incorporate covariance in the data. I'll talk about some theoretical studies and some simulations and real data analysis that we have done with the methods. So this is sort of the standard framework for geospatial data analysis.
Just 1 second. Someone is with the mic open. Can mute maybe this guy? Let me see. Okay, I think you can move on. I think I was able to mute the person.
Thank you. The standard data unit in a geospatial analysis is like a triplet. You have the the response of the outcome variable y, and in this talk, I'm only considering univariate responses. Then you would have like a multivariate set of covariates x. Let's say there are d many covariates, so xi will be like a d-dimensional vector. And then you would also have the information about the location where the data was collected. So this SI would typically be your latitude, longitude. And then the primary goals of the analysis would be to understand the relationship between the outcome y and the covariates x, and then to predict at a new location S naught, because our quantities y are typically, we are interested in understanding not just y at the observed locations, but also how y would be at unobserved locations. So an example is on the right-hand side. So the orange dots are locations in the US where data is collected on fine particulate matter, or PM 2.5. And using data collected in those locations, one can do a geospatial modeling and then predict the levels of air pollution at every location in the US. So the map you see, the colored map, gives you the levels of PM10 at different locations in the US. So the standard linear or generalized linear mixed model for geospatial data takes this form. We relate the response y at location S to the covariates, and then with a random effect. So there will be typically a link function, and depending on the type of the data, the link function can be identity for continuous data, can be log function for count data, or probit or logit function for binary data. And then there will be a linear fixed effect that is modeling the relationship between the covariates x and the outcome y, and the linear coefficients would be beta. And then to account for any structure in the data that is not explained by the covariates x, there is typically a spatial random effect in the data and modeled using a Gaussian process. So if you're not familiar with Gaussian processes, they're simply, if you have data collected at n locations, the spatial random effects WS1 up to WSN is simply a multivariate Gaussian distribution with mean 0 and a covariance C. And the covariance is where we can kind of capture the spatial structure in the sense that if we have two locations, SI and SJ, then the covariance between the random effects WSI and WSJ is simply this C function evaluated at the locations SI and SJ. So this is all multivariate Gaussian distribution, which is kind of very easy to write down and optimize, and which is why Gaussian processes are very popular in spatial analysis. So I really like this framework. I think it has a lot of nice advantages. It kind of separates the effect of the covariates in the fixed part, and then the effect of the random effect of the spatial structure in the random effects. The spatial structure, when it is modeled using a Gaussian process, it can model complicated structures of space because Gaussian processes are fairly flexible. And yet Gaussian processes typically, at least the stationary Gaussian processes, typically would require a very small number of parameters, so like 2 or 3 number of parameters. So you don't need a bunch of different parameters to model a flexible functional space. So that's one nice advantage of Gaussian process, because it kind of encodes the first law of geography, or Tobler's law, which says that things that are closer are more similar, which means that if you collect the random effect at 2 locations, their correlation is going to be stronger if the locations are close to each other. And then another advantage of Gaussian process is that you can use it to predict at any new location. So that would simply come from a conditional Gaussian distribution. So you can predict the W at a new location using something called kriging, and then conditional on the W, you can also predict the response at the new location. So this framework has a lot of advantages, which is why it has been popular in the spatial community for many decades. What is the disadvantage? I think the disadvantage nowadays is considered to be this assumption that the fixed effect is linear. Especially with more data, you want to kind of not use a linear assumption and want to kind of explore if there are nonlinear patterns, and that can help improve your accuracy of your model. And that is where machine learning methods have become super popular because they essentially model a nonlinear regression. So very broadly, machine learning methods, if you're given a covariate y, an outcome y and a covariate x, then it models a nonlinear regression, which is like the mean of y is modeled as a nonlinear function m of x. And how this M is modeled depends from algorithm to algorithm. It's modeled in a different way in random forest, in a different way in neural networks and boosting and so on. But in summary, they're all trying to kind of estimate the best nonlinear relationship between X and Y. So how do you use these machine learning methods for geospatial data? So there have been few different types of approaches here. The first method is called residual kriging. The idea is very simple, that first you kind of ignore that there is spatial dependence in the data, and ignoring the dependence, you estimate a nonlinear regression function using your favorite machine learning algorithm. So you just take y and x and fit a nonlinear function of x on y using either random forest or neural network or whatever you prefer. Then, to account for the spatial dependence, you take the residuals from your fitted model, and then you do kriging on those residuals. So, and this has been called the random forest residual kriging when M is being estimated using random forests. And there have been a couple of papers out there that are fairly well cited. The idea is very simple and it is very easy to use, but the downsides of this approach is that when you're estimating this nonlinear regression, you're completely ignoring the spatial dependence in the data. You're only accounting for the dependence after you estimate the nonlinear regression. Then you take the residuals and then you do the geospatial modeling of the residuals. So your estimation performance is often poor because you're ignoring the spatial dependence, and poor estimation performance can also affect prediction performance later, but the impact on prediction performance is less. It's usually the estimation performance that gets significantly impacted. The other approach is also quite general. What it does is that to account for the spatial structure in the data, it will create a bunch of spatial covariates or spatial basis functions. So this can be either basis functions or just the latitude, longitude, or you can create a matrix of pairwise distances and throw them in as additional covariates in your random forest or neural network software. So you have your original set of covariates X, and then you create your basis functions of your locations, B of S. And so now you're not just modeling Y as a function of X, but you're jointly modeling Y as a function of both X and these spatial basis functions that you have created. And this has been done both in the context of random forest as well as neural networks. This leaves and again, this is a very general approach and pretty broadly applicable. The downsides of this is that it kind of leaves the spatial mixed model framework in the sense that now you're kind of modeling everything together. So you're not doing separate spatial non-spatial effect and spatial random effect. So you lose all the advantages of using Gaussian processes. And what are the advantages of Gaussian processes? It's that you don't need to explicitly create basis functions. You can just write down a Gaussian process model using its covariance function with 2 or 3 parameters. And if there is not a lot of data, then how this method would work is highly sensitive to how you choose these basis functions, as we'll show. Like if you choose too many basis functions, then the effect of the true covariates are going to be drowned out. If you use too few basis functions, it's not going to be able to capture the spatial features. So it needs a lot of careful curation of this set of basis functions for this to work. Or if you have a lot of data, then you can just throw in a large number of basis functions, then it will work as well. So the third approach is what I'm going to be talking about today, is that we keep most part of this spatial generalized linear mixed effects model same. We just want to relax this linear regression part and put in a nonlinear function of x. Everything else is, we are going to keep everything else to be the same. So the link function is going to be the same. It's if it's continuous, which is what we'll focus on today, the link is going to be identity link. But if it's binary, we can use like a probit link. We will still continue to use the spatial random effect as a Gaussian process. So we'll retain all the advantages of a Gaussian process. The only thing we are changing is that instead of doing x beta, we do an m of x, where we want to estimate this m function using either a random forest or a neural network. So as I said, this is the only change. It keeps the Gaussian process and retains all its advantages. It still separates the effect of the covariates and the effect of the space into two different components. And so if there is not a lot of data, using Gaussian processes is useful because you only need 2 or 3 additional parameters to specify these random effects. And you can predict at new locations using Kriging in the same way you do in the GLMM, but instead of a linear function, now you just use a nonlinear function. Everything else is going to be the same. The only question is, none of the existing machine learning software has the capability to do this. They would do it either in one of the 2 other ways that I mentioned. So how do we kind of create a method where you can use this m function as a nonlinear function, model it using a random forest or neural network, while still using a Gaussian process to model the spatial structure? So there has been some recent work in this area. So some of it is done by our group. So we have done the extension of random forest to spatial data that I'm going to be talking about today. We have also recently extended it to binary spatial data that is on archive. Fabio Segrest in Lucerne, he has extended gradient boosting with the same idea of using Gaussian process for the random effects and a gradient boosting for the covariates. And this was published in JMLR in 2022. And then we have also recently extended this to neural networks. So some recent work emerging in this third way of modeling using machine learning while keeping Gaussian processes for geospatial data. So I'm going to be primarily talking about these 2 papers, the random forest approach and the neural network approach today. So first I'll be talking about random forest. So our paradigm is Y is continuous data. So the link function is identity. The link function goes away here. And what we want to do is we want to change the x beta with an m of x, where we want to estimate this m using random forest. Everything else is same. You have a Gaussian process, spatial random effects, and you have some nugget effect or like measurement error that is typically there in the geospatial model. So how do we do this? So to kind of figure out a new random forest algorithm that will account for the Gaussian process covariance, we go back to the linear model and see what is done there. So if we go back to this spatial linear mixed effects model, we can merge together the spatial random effects W and this noise terms epsilon star into a single error term epsilon, which is the sum of these 2 things. And the covariance of epsilon is going to be the covariance matrix coming from the spatial part and the covariance and the diagonal variance matrix coming from the noise part, right? So we can just sum up this as covariance of epsilon is C plus tau squared times identity, and we call this the sigma matrix. And so we can equivalently write this hierarchical model as this marginal model, where Y is normal with mean x beta and variance matrix sigma. And if this variance matrix sigma is known or conditional on the current values of the parameters of the sigma matrix, the best estimate of beta is given by minimizing the log likelihood, the negative log likelihood, which is equivalent to minimizing this generalized least square loss. because if you write down the multivariate normal log likelihood, you will get this term here. So conditional on sigma, the best estimate of beta is given by minimizing this quadratic form, which is commonly known as the generalized least square loss. So now how do we do this for random forests? The model is different in the sense that instead of x beta, we now have m of x, and we want to estimate m using random forest. Everything else is the same. Your sigma is sum of your Gaussian process covariance matrix plus your noise covariance matrix. The only thing is the random forest estimation needs to account for this covariance matrix sigma. So let's look at what random forest really does. So random forest is a collection of regression trees. A regression tree is a tree estimator of a nonlinear function connecting your observed covariates x to your response y. So to illustrate, suppose you have two covariates, x1 and x2, and these are the values of the two covariates. The locations give you the values of the covariates. And suppose you have an outcome y, the color of the points give you the value of the outcome y. Random forest want to estimate, or a regression tree will estimate a piecewise constant function that best describes the relationship between y and x1 and x2. And to do this, it will start with the whole covariate domain, which is 0, 1 times 0, 1, and it will then sequentially split into smaller rectangles. So it will start, say, by splitting for x1 less than 0.2. So it will split it into two halves. And then it will, again, further split this by x2 less than 0.6 or x2 greater than 0.6, and so on. So it will do this recursively. And at each stage, what it does is that suppose you're in a rectangle and you want to split the rectangle to create two sub-rectangles. What it will do is it will calculate the variance of the outcome in that bigger rectangle and the pooled variance of the outcome when you create two sub-rectangles. And it maximizes the variance difference between this a parent node in the tree and the two children nodes, the right and the left children nodes in the tree. And so basically it will pick a partition that gives you the highest value of this quantity, which would kind of mean that you will create two nodes where the outcomes are very similar within the nodes and very dissimilar between the nodes. That's the idea. That's why they use this loss function. So to formally summarize, so it will kind of start with the whole covariate domain and it will kind of sequentially split into small rectangles. Once it creates a set of final rectangles or leaf nodes, the value of the function in that leaf node is simply going to be a constant, which is the mean of the y values that are within that leaf node. So this is what a regression tree is. And then a random forest is just a collection of an average of many regression trees. Each regression tree is created using a different subsample or resample of the data, and this is called bagging or subsampling. And then when creating the regression trees, random forest kind of looks at, so it doesn't look at all covariates, it only looks at a random subset of covariates to select where you will split your node. And so it's called a random feature selection. But the main idea is you sequentially split the nodes and you split them using this loss function. That's the main idea. So now let's look at the issue of random forest or regression trees for spatial data. So this is the same figure, same set of points that I showed previously, and then I highlight two different points here. So these points are quite far apart in the covariate values, right? For the red point, the x1 value is large, the x2 value is small. For the blue point, the x1 value is small, the x2 value is large. So they are quite far apart in the covariate domain. And it's likely that when you do a regression tree estimator, they will be in different nodes and they will not inform each other. Now, this was a data set, but there was also a spatial component to it. And so it was actually a three-dimensional data set. So there is now x1, x2, and the space. And I have rotated, this is the same set of points, but now I have rotated this and to show the 3D orientation of the points. And you can see how close these 2 points are in the space domain, space axis. So these 2 blue and red points are the same points here. It's just now we are showing the actual 3D plot and rotating it in a way to kind of see how their space coordinate are. And you can see their spatial coordinates are extremely similar. They're very close to each other. So that kind of shows that even if 2 points are very different in their covariate values, they may be collected at very close locations. And the random forest does not consider this spatial similarity when creating these rectangles or partitions. So this blue point is not going to be informed by the red point because every node will just have the mean of the y values within that node. And so they're even if they're collected at very close spatial locations, that's not going to be used in the algorithm. So how do we extend it to actually use the spatial covariances? The key idea is that this loss function that we see here that is maximized in a random forest, it's called the regression tree split criteria. This is equivalent to minimizing an ordinary least square loss, y minus z beta square, where z is a design matrix whose ijth entry gives you whether the covariates in the ith data point belongs to the jth node or the jth rectangle. So it's a binary design matrix which just gives you which data point belongs to which node. And splitting a node is equivalent to minimizing this least square loss over both beta and where you split the specific column of the design matrix. And so basically you can write down the regression tree split criteria as an ordinary least square loss. And you can also write down the estimate, which is just the mean of the node, as an ordinary least square regression coefficient. So that's the key connection that we can characterize how splitting is done in a regression tree to sort of a linear regression, but the linear regression is using the node memberships, not the actual x values. Once we have this characterization, the idea to incorporate covariance is simple. We have the covariance matrix sigma. So instead of using the ordinary least square loss, we will just use the generalized least square loss using the Gaussian process covariance matrix sigma. In practice, sigma is usually not known, so it's kind of estimated. So we use the estimate of sigma. Here, we call sigma hat inverse as Q. And we call this loss function the dependency adjusted regression tree, or the DART split criteria. And you can see that it explicitly uses information about the covariances between 2 data points when you do the splitting of nodes in the random forest. And once you split the nodes, your estimate of beta hat is now just the generalized least square estimate. This again comes from the fact that the minimizer of this quadratic form with respect to beta is just this thing. So it's kind of a direct analog of what we do in linear models. When you have a covariance matrix, we do not use this loss function. We would use this loss function, the generalized least square loss function, and we do the same thing in random forest. When we have a spatially dependent data, we use the generalized least square loss for node splitting, and then the node estimates just become the GLS estimates. So what is the advantage of the GLS versus OLS loss when you are creating a regression tree for spatial data? So here is an example. The true function is a nonlinear function, but it's a simple one. It's just a piecewise constant function, but given by this orange dashed line. So it's like constant up to a value of half, and then again a constant with a different value from half to 1. So there's a jump. So it's a nonlinear function. And then if we want to use a regression tree, we would expect the regression tree to identify where to split the domain, because there's a clear partitioning where the clear sort of idea where the partitioning should be done, because you should partition around half, and then use the mean of the values before half as the estimate of this part and the mean of the values after half for the estimate of this part, right? So now we look at where the loss function is maximized for both the OLS, which is the blue, and the GLS, which is the red. And they're both maximized around half, which is good because that's where you want to split the node. But then if you look at the uncertainty associated with each of these, the GLS has much narrower uncertainty given by the brown band, and the OLS has a very wide uncertainty given by this very wide blue band. And this is the same thing that you see in linear models, that if you have dependence in your data and you ignore the dependence, you will have higher uncertainty. Whereas if you use the covariance that matches the dependent structure, you get more efficient estimates. So it's the same sort of pattern we see when going from a linear model to a regression tree using the GLS loss. Once you do the estimation using this GLS loss, you get an estimate of M. Let's call that M hat. And using M hat, it's very simple to predict at new locations in RFGLS using kriging. So to see how to do that, let's go back to the linear setting. If you have a linear model, your prediction at new location where you have a covariate X new is simply X new beta plus this kriging component. When instead of a linear model, you have a nonlinear model M, it simply becomes you replace the X new beta with the M hat X new and the X beta with the M hat X. That's as simple as that. And you get kriging predictions at new locations. I want to show one slide on simulations to kind of demonstrate how it does compared to the other two styles of modeling spatial structure using random forest. So the random forest residual kriging is the green line. These are giving the mean squared errors. The random forest residual kriging is the green line where you do not use any spatial information during the estimation. It is only used subsequently during the prediction. The spatial random forest is the yellow line, which uses a bunch of basis functions as additional covariates in the random forest. And the black dotted line is the RFGLS. So we kind of standardize it to be at 1 by dividing the MSEs. On the x-axis, we have the strength of the spatial random effect variance. So higher the sigma square, the stronger is the spatial random effect in the data. And we see that when sigma is small, RFSP performs very poorly. And this is because it performs even worse than the residual kriging. And this is because it creates a bunch of spatial covariates. And if the spatial signal is weak, so it's basically creating a large number of covariates for something that does not have a strong signal in the data. And it drowns out the true covariates, which are the non-spatial X's, because random forest randomly selects a subset of the covariates, so it will tend to select the spatial covariates more and more. So basically, if you use RFSP with a large number of basis functions, it's going to perform very poorly. The RFRK does well here because there is not too much spatial signal in the data, so ignoring it is not that bad. But on the other hand, when there is a lot of spatial signal in the data, the RFSP does really well because it is using a bunch of basis functions and they are useful in this case. So it does well. The RFRK, which ignores the spatial information completely, does poorly. But the RFGLS consistently does better than all of the methods in all of the scenarios because it is modeling the spatial covariance using Gaussian process, and the estimate of the decay parameter in the Gaussian process can adapt to the strength of the spatial signal. So if sigma square is high and the spatial correlation is high, its estimates are also going to be high and it's going to perform well. If they're low, its estimates are also going to be low and it's going to perform. So it performs well at both ends of the spectrum and outperforms both of these methods. So the theory of random forest is still kind of a work in progress. Very recently, I guess not very recently now, but in 2015, there was a seminal paper which kind of did theory for random forest for IID data. So we basically adopted that theory, but kind of extended it to kind of consider dependent data. And we showed that we could have consistent estimates of the mean function when using RFGLS. And some examples where the theory holds is that if you have spatial matter and Gaussian process on a one-dimensional regular lattice as your random effect and a nonlinear mean function as your fixed effects, autoregressive time series is another example where the theory holds. And we were also able to show that just the naive random effect, random forest, where you ignore the spatial covariance, is also going to be consistent, but it's an inefficient estimator. It's the same way the ordinary least square is consistent under dependence, but it's inefficient. So we see the same thing here, that the naive random forest is consistent under these dependent settings, but in our data analysis, we always see it to be performing much poorly than the spatial random forest. There is a package for this. It's called Random Forest GLS. There is a vignette created by the student who developed this method, how to use random forest. If you go on CRAN, you can see this. I think it works for data sets of around like 1,000 to like maybe 5,000. It's generally a little bit slow. So if you have bigger data sets, you would not be able to get this to work currently. Our hope is we'll make the method faster in the future. But if you use it and find it useful or come across any issues, please let us know. But the fact that it was not super fast was an important concern, and which is why after we did this extension of random forest, we kind of looked at what other machine learning methods we can try using the same idea, and then we kind of came across neural networks, which are super fast. And so the next part of the talk is presenting a same idea or similar idea, but for using neural networks instead of random forest, that allows you to kind of analyze much larger data sets with these type of GLS losses. So the neural network is basically, for regression task, is basically a specific family of nonlinear functions. So if you're modeling y as a nonlinear function of x, a single layer feed-forward neural network or a single layer perceptron is basically this specific nonlinear function of x. So you have a linear transformation of x using the weights w. Then you pass through a nonlinear transformation called the link function or activation function. And then you again pass through a linear function. So it's like two layers of linear transformation sandwiching a nonlinear transformation. The linear weights are unknown and those are estimated. The nonlinear function is assumed to be known. It's typically like the sigmoid function or a hockey stick shaped function called the ReLU. And so that is basically the neural network function class. And this is it is called the output layer, and you kind of match this output layer to your outcome using least square law. So this is sort of a schematic of what neural network does. So you have your covariates, which are like D different covariates. You pass it through this weights W to get this layer Z. Then you pass the Z through this function G1, which is a nonlinear thing, to get this hidden layer A. And then finally, you do another linear combination of A's to get this output O, and you match O with I, and to estimate this parameters beta and W1. So that is it. It's just a very specific family of nonlinear functions. But if you use a large number of nodes in this hidden layer, this class of nonlinear functions would approximate any continuous function. This comes from this universal approximation property of neural networks. So that was a one-layer neural network. You can do this, apply this idea recursively to get an L-layer neural network. And it's exactly the same thing. You start with your XS and then alternate between linear and nonlinear transformations. And instead of doing this just once, you do this L times to get your Lth hidden layer. And then you finally do one linear combination to get your output layer. So in this like L layer or multi-layer perceptron, there will be L sets of W matrices and one beta, which are unknown. All the nonlinear transformations are known. And how is estimation done? It's just simply matching this output layer O to the observed outcome Y. And so O is this class with all these parameters. So then you kind of take the derivative of this loss function with respect to the parameters. And instead of trying to do full optimization, what they do is called a gradient descent, where they kind of update each parameter by a little bit using the gradients. The reason why neural networks are super popular for such tasks is because of some computational properties, especially this thing called mini batching or stochastic gradient descent, which is that instead of using this full loss function, which goes over all the data points going from 1 to n, what it will do, it will create small subsets of the data called mini batches. And at each time point, at each iteration, it will only use the loss corresponding to one mini batch of the data. And it will do the gradient descent using the mini batch loss instead of the full loss. And then it will cycle over all such mini batches and kind of proceed like that. And stochastic gradient descent is a specific case of mini batching where the mini batch size is 1. So at each iteration, you will only use one data point to evaluate the loss, and then you'll cycle through all data points. So that makes the evaluation of the loss function much simpler, especially if you have large data sets, and it becomes much fast, and which is why it's very convenient to use neural networks for this task. The downside is for our spatial setting, we are once again, the standard neural networks once again would use this ordinary least square loss, so it is not going to be accounting for any dependence in the data. So our idea is very similar to what we did in random forest, in the sense that instead of using the ordinary least square loss, we want to use the generalized least square loss with the Gaussian process covariance in between. But the issue is that once we do this, we kind of lose all the advantages of neural networks, in the sense that evaluating the sigma inverse is very expensive in Gaussian processes. For n locations, it will typically take order n cube many operations. And when you kind of introduce this dense sigma in the middle, you lose the property that your loss function cannot be broken up into sort of sum of loss functions corresponding to mini batches. So the GLS loss is not amenable to mini batching. And then the last piece is that the sigma matrix will have the unknown Gaussian process covariance parameters theta. And so we would need to estimate that in addition to estimating the parameters of the mean function m. So we have a nice result in this neural network paper where we show that if we use the sigma as a nearest neighbor Gaussian process covariance matrix instead of a full Gaussian process covariance matrix, the resulting neural network optimization or the resulting neural network structure becomes same as a graph neural network. So to illustrate what I mean by that is, what I mean by NNGP is that we know if we know the full Gaussian process model, we can write down the likelihood of y as product of this conditional likelihoods. Yi, there should be a conditioning sign here. I don't know why it's not showing up. Yi given y1 up to yi minus 1. So Vecchia, in his seminal 1988 GRSSV paper, said that given that spatial correlations are only high at close by locations, it's enough to condition on just a small set of nearest neighbors instead of using all of these going from 1 to I minus 1, which will be very large for large I. And that change reduces evaluation of this likelihood, the computation for evaluation of this likelihood from cubic to linear in n. And there is now a lot of work on this Vecchia's approximations, especially like how the approximation depend on the ordering, and then how it's sort of it can be generalized to many different Gaussian process approximations. What we did in the nearest neighbor Gaussian process paper in 2016 in JASA is that we kind of showed that Vecchia's approximation corresponds to a valid probability distribution in the sense that this likelihood, this approximation that you get here is not just a good approximation for the full GP likelihood, but it's a valid multivariate normal distribution by itself. And with that property allows you to extend this approximation to a valid Gaussian process over the entire domain, which we call the nearest neighbor Gaussian process. And the advantage of having a valid Gaussian process is that you can use it in any Bayesian modeling. You can replace your Gaussian process prior with an NNGP prior and do your Bayesian inference the same way as you would do normally, but in much faster time. The other property of this nearest neighbor Gaussian process that we'll use in the context of neural networks is that the NNGP sigma inverse is sparse, and it has a sparse Cholesky factor, which is equivalent to having a sparse directed acyclic graph among the locations. So just to clarify, if basically the location J belongs to the neighbor set of location I, or location I belongs to a neighbor set of location J, the Cholesky factor of sigma inverse will have the ijth component to be non-zero. Otherwise, the Cholesky factor will have it to be zero. So it gives a very sparse Cholesky factor for the sigma inverse, which can be summed up in terms of this directed acyclic graph. So for example, location 6 has location 1 and location 3 as neighbors. So we see arrows going from 1 to 6 and 3 to 6. It does not have location 5 as a neighbor, so there is no arrow going from 5 to 6. So why is this important in our context? So if we use this NNGP covariance matrix in our GLS neural network loss function, a GLS loss between Y and O with a covariance matrix sigma inverse is equivalent to an OLS loss between Y star and O star, where Y star is the Cholesky factor of sigma inverse times Y, and O star is the Cholesky factor of sigma inverse times O. So this is just like a straightforward linear algebra, but what it means is that if you look at what this decorrelated response Y star looks like, it will only involve information from the same node. So for example, here, the node 3 has neighbors 1 and 2. So Y star 3 will only be a linear combination of Y3 and neighbors of Y3, which are Y1 and Y2. So it's the decorrelation operation using nearest neighbor Gaussian process is a linear combination of the neighborhood of the graph, of the directed acyclic graph in the NNGP. And the linear weights are simply driven by the nearest neighbor kriging. So decorrelation in NNGP is equivalent to convolution on the nearest neighbor graph with kriging weights. And if you look at what graph neural network is, a large subset of methods of graph neural network uses graph convolution, which is basically you start with a graph valued object and then you kind of do an averaging or linear combination of your nodes to create the next stage of the graph. And NNGP decorrelation with NNGP does exactly that, because when you're multiplying by the sparse Cholesky factor, it's equivalent of aggregating over the graph with the weights given by kriging weights. So why is this kind of any importance? It is because basically we were originally thinking of doing a GLS loss between Y and O, but now we kind of do the decorrelation step in between to create the Y star and O star, and we just do an OLS loss between Y star and O star. So the advantage of doing OLS loss is that it can be split into mini batches, and so we kind of gain back all the like fast computational properties of neural networks. So even though we are doing actually a GLS loss between Y and O, it becomes equivalent to doing a OLS loss between Y star and O star when our covariance matrix is an NNGP covariance matrix. And so we just do mini batching in the same way we would do for standard neural networks. The spatial covariance parameters theta, which are unknown, are only present in these graph convolution layers. So they can be updated as part of the estimation process. So what we do is with the X, we get the O, and those are the multi-layer perceptron parameters. So those parameters are there in these layers. And then when we do the decorrelation in these two layers for the response and for the output, those are the layers where the spatial parameters are there. So all parameters are in some layer or other of the neural network, and we can update all parameters together. And then once we estimate the neural network, kriging is also very simple. So if we get covariate at a new location, S new, we first pass this covariate X new through our trained neural network to get the output. Then we use this, then we add this new location to our nearest neighbor graph and get its neighbors. So in this case, the neighbors are S5 and S4. And so this output O is now convolve with its neighbors to get the convoluted output O star. O star is our estimate of our convoluted outcome Y star. Now we have Y star, we have Y5, Y4, and we want to predict this Y new. Now we know that Y star is a convolution of Y new and its neighbors, Y5 and Y4. But here we kind of need to go the other direction because we know these three things and this one is unknown. So this is a deconvolution step that we do to get the predicted response at a new location. And we can show that doing this within the graph neural network is exactly equal to predicting at a new location using nearest neighbor Gaussian process with the nonlinear mean M modeled as the neural network. So the summary, the idea is same as the random forest in the sense that we just introduced this inverse covariance matrix from a Gaussian process in the optimization process, but the implementation is very different from the random forest in the sense that we kind of frame the whole process as a neural network, as a graph neural network using the NNGP covariance matrices. And then we can kind of do mini batching as well as kind of estimate the spatial parameters within the same framework, and everything kind of gets done within linear time complexity. We also did the theory for neural networks. I'll not go into too much details here, but we were able to show that if you have data from a spatial matter GP on an irregular set of locations with a nonlinear mean, and you use NNGLS, you do get consistent estimates of the mean function M. And the consistency holds even when you kind of use the NNGP covariance instead of the actual full GP covariance. Some simulation results. So for estimation of the mean function, we compared the non-spatial neural network and the GLS neural network that we propose. The other methods which kind of do either add the latitude, longitude, or add a bunch of splines will not give you a separate estimate of the mean function. It gives a prediction jointly as a function of the covariates and the spatial basis functions. So we have like 5 candidates for the prediction. And so for estimation, we see, of course, we do much better than a non-spatial method because it does not account for any spatial dependence. For the prediction, we again do much better than most of the methods. The only one that kind of does slightly close to ours is the residual kriging, where you kind of ignore the spatial dependence during the estimation part, and then you do kriging on the residuals. That does better in this case. Better than the other methods, but not better than ours. These are the runtimes as a function of sample size, and you can see that these are all like different components of our method. The yellow is the total runtime, and you can see that it scales linearly with sample size, which is good, which kind of agrees with the theoretical runtime complexity. And then we finally use this to analyze the PM2.5 data in the US. The covariates were temperature, relative humidity, total precipitation, pressure, and wind speed in the 2-axis. And these are the prediction performance on holdout data. Again, our method does the best, but the spline method also does really well. whereas the non-spatial method does really poorly because it does not account for any spatial dependence. Just a summary slide. There's a lot of increase in popularity of these machine learning methods for spatial data, but if you have spatial covariance, spatial dependence, and if you don't use information on spatial dependence in your method, you're going to end up with results that are probably not very accurate. And so RFGLS and NNGLS are extensions of random forest and neural networks that explicitly codes the spatial covariance into the model using the GLS laws. It is kind of embedded within this traditional spatial mixed model framework, so you get all the benefits of using Gaussian processes, like only having to estimate 2 or 3 covariance parameters. You can do kriging at new locations. For the neural network, I think its representation as a graph neural network is interesting and possibly of independent use beyond this current work. And we did a bunch of simulations where the performance of the method is fairly robust. And we also did some of the first theory for machine learning methods under dependence. Some future work, I think the graph neural part is very exciting, and we want to kind of explore this more. One thing is like for aerial data sets, for example, where we already use graphs in this kind of intrinsic autoregressive models, a natural candidate would be to kind of use this graph neural network type approaches. And also for multivariate responses, instead of using kriging weights, then kind of the low-hanging fruit would be to use co-kriging weights and see how we do there. And then currently we only used stationary Gaussian processes, but the method in concept works with non-stationary Gaussian processes as well. So if there is a lot of non-stationarity in the data, we can either use a non-stationary covariance, or we can kind of add like some basis functions in the covariate set while still modeling the covariance through a Gaussian process. And then the most challenging part is how to do uncertainty quantification of the mean function estimation, because this is not a Bayesian implementation, where the implementation was very sort of optimization based. So we have been doing some basic resampling kind of approach to uncertainty quantification, but it's not very computationally efficient, and it's also not like backed by much theory currently. So that's definitely another big area going forward. This is the neural network work is developed by Ventao, who is a 4th-year PhD student working with me at Johns Hopkins. The random forest, the 2 papers are led by Orko, who is a current postdoc at the University of Washington. He was my former PhD student. And Shumanto, who is my collaborator from Cornell University on the random forest paper. And this work was supported by grants from the NSF and the NIH. This is the neural network paper. This is the random forest paper which was published. This is the random forest software. Please use it and send us feedback. And then I didn't get to talk about the binary spatial data, but it has its whole different methodological innovations. If you're interested, please read this archive paper. Thank you.
Thank you, Abhi. Great talk. We have people also on YouTube, so if you like to ask questions on YouTube, I can go there and check. Just saying, so they have a chance to write on chat. I'm there. I have a few questions, and I'll first open to the public. If they feel like asking anything, please just open the mic and maybe do a question.
Can I ask a question?
Yes.
So thanks a lot for the nice talk. I was going to ask about uncertainty quantification if you were doing that, but then you answered in the very last slide. But still on that, have you made, I don't know, maybe the less hard way would be to try to do some kind of central limit theorem to have asymptotic confidence intervals or something like that? Because I mean, if you try MCMC, it is going to be, I mean, the cost will be crazy. Have you started looking at stuff like that?
Very good question. The reviewers of the neural network paper have also asked the same question. Well, I don't think there is a central limit theorem for pointwise pointwise estimates of the mean function. There will be central limit theorems if you average the mean function over your entire set of covariates. But that is not really very useful because we do want to make pointwise predictions, right? So even in the context of IID data, we have been looking at it for the past couple of months after the revision invite came. We haven't found anything that sort of has the central limit theorem for neural networks, even in the context of IID data. That is pointwise central limit theorem. There are central limit theorems for averages of the mean function, which is part of the reason we are currently doing just some simple bootstrapping. But one promising idea is that there is this concept called dropout, which is basically when you estimate the parameters of the neural network, you kind of randomly make certain parameters 0 at every iteration. And that will give you a bunch of different predictions by making different parameters to be 0. And there is some work saying that that dropout essentially corresponds to a variational Bayes approximation. And so it gives you a crude uncertainty estimation. The approximation is very crude, so I don't know how well it works, but that's definitely a little bit more promising than kind of trying to get a central limit theorem, I think, here. And again, I agree with you that full Bayes is probably not feasible because there's just so many parameters here.
I mean, any direction is going to be a hard problem. And
yeah, it's a very good question. Thank you.
Thanks.
Okay, so I have some basic questions, I think, just conceptual. Two of them. So you have this structure where you put, say, a random forest. You like to put an M function within the GLM framework, right? But then if you're not in a linear kind of problem where you use the identity link, your H function is already nonlinear. And you have a nonlinear within a nonlinear. First, how to interpret that? That's one first question. And then just to get it together, can you separate the HM of X, say just as M of X, let the machine estimate whatever it feels like, and just apply the link function over the random effects? That way, the link function is there just to transform to the whole line, because that's basically what it's doing, right? And then you can use your traditional methods to do the estimation, and let the machine, or not the machine, but at least the method itself just do estimate H of M. That will be what we'll do, right?
Yeah, that would have been possible if like H is a function such that H of M plus W breaks into H of M plus something of W, but that is
product, right?
Yeah, like a product, but that is typically not the case. Like if you think of, so we have done this for binary data where we use a probit link, and at least for probit link, you can because it's a known link, like H is a known function where M is unknown, right? So, and the probit link is invertible, so you can actually estimate M, at least for the probit link, and that's the binary paper work. I don't know if there is a way to kind of separate, because again, I'm thinking of going back to the linear framework and see if there is a way to separate there, because if there's a way to do it in that linear setup, then we can also do it in the nonlinear setup. It's definitely an interesting idea. I haven't thought about this, but I have to give it more thought. At first, my first reaction would be, you can do it for some specific links, which kind of becomes kind of product kind of thing. But neither the probit or the logit has that property. Maybe the log would be better. No, log is not going to be able to do that.
You can separate as products, right? Exponential of something.
But log of product is sum of something. But here we have sum of something, and we want to make it a product. So yeah.
Well, but so then it comes to my second question. If that's possible, which honestly I don't know either, interpretability of this, whatever, random forest, neural networks, it's always something challenging in some sense. And then they have those methods, say, to give the importance of the random forest variable, so on, but it will give you the importance of the variable over the transformed space. So that was why I was thinking, if you can just separate that to give you at least on the response space, you get you get directly to interpretation of that importance, right? If you try SHAP or any other method like that, again, you will have the contribution of the variable like we have, but it's not a beta structure. So the SHAP and the other is not like, oh, I put logint and then I have the odds ratio kind of interpretation, because they come up with some machinery to give some approximation of what is a linear interpretation, but it's not a kind of beta thing that you can just put in the equation and solve. So how do you get very nice prediction, you improve prediction, that's very clear, but how do you interpret those? If you like talking to a doctor, medical doctor, what do you tell him?
Yeah, very, very good points. I think, again, this is again, like, I think we are at the very kind of early stages of this work, so a lot of things need to be explored. What we have currently done, and again, we did it mostly in the setting of the continuous outcome. We have looked at like partial dependence plots, which is like you get the estimate of m, but it's kind of hard to visualize when x is more than 2-dimensional, right? So we kind of do integrate out all but one of the covariates and get that estimate of that integrated function, and we can plot that and see which of those have the most variation along that covariate. So we have done partial dependence plots, and then you can do the variable importance using either, for random forest, there is the permutation-based variable importance, where you kind of permute a covariate and then fit the random forest and see how much its MSE increased. And the more increase it is, the more important that covariate was, because that you lost that importance after permuting. So we do the permutation, we can do the permutation-based thing. We haven't tried the Shapley values in this one, but there is also the concern, as you mentioned, that with a nonlinear link, the interpretation will be at a transform scale. I agree with you there. So I guess I don't have a good solution to this right now. So it was like this was primarily focused on estimation and prediction. I think the next steps are like the uncertainty quantification and variable importance going forward. Yeah.
Finally, spatial statistics, sometimes estimating the parameters of the spatial setting is already challenging. Bias, if you get nugget very big and the spatial signal small, things get a little bit wild in the estimation. I assume this carry on because it may be
absolutely
worse, right? Because
it carries on. I do think it gets a slightly worse because you kind of the machine learning methods tend to kind of overfit to the data. So you will kind of often what we have seen so far, we get slight overestimation of the nugget because it's kind of losing some of the spatial structure. It tends to sometimes explain the spatial variation as a covariate effect, because it's there is sometimes suffer from a little bit of overfitting. Generally, it's not that bad. So overall, we still see the parameters to have the similar order of magnitude, but even in the linear case, it's a very hard problem, and only certain combinations of parameters are only identifiable. We know that, right? So yeah, so those problems are there. It doesn't go away.
So I know there's a lot of discussion on spatial confounding, if it's useful or not. I know you've been there. Do you think spatial confounding also plays a role here? Because these functions are extremely flexible, right?
Yeah.
So if the X has any spatial pattern that is not even related with the covariate itself, it will just learn some structure from the data. You can assume like, oh, if I apply this M on X, it will have a nice relationship. So you basically create the confounding there in some sense.
Yes.
And then the random effect gets a little bit. So what does that mean as well?
So if you have an X that has a spatial structure, we would not be able to identify the M function in that case, because it's can be explained by the M function, can be explained by the random effect. So if your X is non-spatial in nature, then you can hope to identify the effect of it. If it is like purely spatial, I think it just acts as another spatial term in the data. So I agree with you. We would not be able to identify it. But I think the confounding resolves are always assuming that the exposure varies at a finer scale than the confounder, which kind of is equivalent to assuming that there is some non-spatial structure in your X. So if there is a non-spatial structure in the X, then you would be able to identify.
Okay.
Yeah.
Okay. I don't know if I talked a lot. So if anyone has any other question, otherwise, let's thank Yabi again for his time. I know it's lunchtime over there. So let me see. Let me see on YouTube a little bit. Okay. We don't have questions there. So thank you, Abi, for your time. Very interesting work. This is the kind of very nice work where still a lot of to do because, you know, you
Yes,
enter in a new
absolutely.
area, a lot of things to explore. So thank you for your contribution, for your time. It was a pleasure to have you here.
Thank you so much for inviting me. It was really lovely to end up getting to present. And thank you for the question.